Swayam Prabha. Digital India. Educated India.
Okay, now let me give an example which shows a variation in how mathematical induction is used. So far we've been talking about this as a way to prove claims about integers, about positive integers, right? Claims like n cubed minus. But here is a seemingly very different kind of claim you can prove using mathematical induction. So this is about something called Trominos, like dominoes are a pair of tiles stuck to each other. Trominos is these three tiles stuck to each other like this. Okay, and the claim is that you can use these Trominos to tile a grid of 2 to the n by 2 to the n squares, and in which one cell has been removed. Okay, so if you look at the Tromino, that itself actually fits that description. It's a 2 by 2 grid, right? So there are 4 cells of which one cell has been removed. Okay, so for n equal to 1, this 2 to the n by 2 to the n grid, punctured grid, is the same as a Tromino. I've drawn the Tromino showing cell at the lower right corner being removed, but you can turn the Tromino around and you'll see that any of the 4 cells could have been removed and you'll still get this Tromino. So I'm going to allow you to rotate your Tromino while doing the tiling. So the base case is indeed n equal to 1, right? So you have 4 possible ways a punctured 2 by 2 grid can look, and in all cases you can tile it using this Tromino, just one copy of the Tromino. So tiling here means that you can cover every square in the cell, and so you take a bunch of Trominos and you arrange them on top of the grid such that every cell in the grid is covered by exactly one Tromino, and no 2 Trominos overlap, and the Trominos don't stick out of the grid either, and they leave the punctured position uncovered, right? So they cover only the unpunctured cells of the grid. Okay, so for n equal to 1, here is a proof by picture of that you can do this tiling. How do you do it? Now we would like to use induction. We'll say, okay, take some k, right? Any k greater than or equal to 1, and suppose that the claim holds for n equal to k. I'll prove that the claim holds for n equal to k plus 1. Okay. So how will I do that? So what I'm going to do is, what do I need to prove? I need to prove the statement holds for n equal to k plus 1. So I'm supposed to look at 2 to the k plus 1 by 2 to the k plus 1 grids which have one cell removed. So give me any such grid, right? Punctured grid. I have to show you how to tile it. I have to show that it can be tiled. What I'm going to do is break this grid. So here there's an example with k equal to 1, so k plus 1 equal to 2, right? So this is a 4 by 4 grid with one cell removed. What I'm going to do is split this grid into 4 parts like this, where each part is a 2 to the k by 2 to the k grid, and one of them is punctured. The others are not going to be punctured, right? Exactly one of them is punctured. But then I'm also going to remove from, or you could think of it as place a Tromino here in such a way that, so I'm placing it in the middle, the 2 by 2 grid in the middle, and I leave, so there are the 3 tiles in the Tromino is going to be on 3 different the subgrids. And the subgrid that I choose to not cover using this Tromino is the one in which there is a punctured cell. So remember again, of the 4 subgrids, exactly one of them will have a punctured cell. That's the one I'm not going to cover using my Tromino. I keep my Tromino such that it covers one cell of each of the other subgrids. And then, if you think of these covered cells as being removed, what I need to further cover is, so this one is a punctured grid of size 2 to the k by 2 to the k. And if you look at this one is also now a punctured grid of 2 to the k by 2 to the k. The puncturing happened because of the removing of this one cell in that grid. And same with the other two also. So in all 3 of these cases, also you have a 2 to the k by 2 to the k punctured grid to be covered, and this covering you can do using the induction hypothesis, right? So the induction hypothesis implies that there's a way to cover all of these things, and then you are left with covering, and combine that covering with this one Tromino you put in the beginning, and you get a complete covering of the whole. Okay, so that is a proof. Let me show you, just for illustration, one more example for k equal to 2. So k plus 1 is 3. So there's a 8 by 8 grid, and the induction, the step being illustrated here shows breaking up your grid into 4 parts, and then you put a Tromino such that it leaves alone the grid where there is the punctured cell appears, and it takes each of them, one covers one each, the other 3 grids. Now, I could stop there and I could say, by induction hypothesis, this is there is a covering for this. But just for fun, let's continue his argument and let's see how are we going to cover this, each of these 3 things. So you could actually, continue this argument, unroll this inductive argument, and get an algorithm for tiling. So let me illustrate that. So actually, let's go back to this case of the k equal to 2 case, or rather k equal to 1 case, right? K plus 1 equal to 2. And so you're left with the case of k equal to 1 as the 4 subcases. And for those, I know how to tile them using, looking up from here. So this one looked like this, so the tile would look like that, right? And this one here looks like the punctured grid here, so I'll have to put a tile there, and so forth. So I tiled the 2 by 2 grids by looking at the solution. This is the base case, right? But how about here in this case? I have to tile each of these 4 by 4 grids, and for that I'm going to continue making this argument by saying, okay, how do I tile this one? I will do it kind of what I did here. Break it up into 4 parts, put my Tromino tile in such a way that it leaves out the one that already had the punctured cell, and then I can cover, I can tile the remaining with the base case. And I'm done with that one. Then I move on to the next one. I break it up into 4 parts and put my Tromino in a way that avoids the one that's already punctured, and then use the base case to cover each of them. And similarly for the other grids, right? So this actually, I just had this proof here of the inductive proof, and I could derive an algorithm for tiling from that. This is something we will revisit later when we talk about recursive algorithms. But the point I wanted to make here with this example, among other things, is that it's a structured problem where you're not just talking about the property of numbers. Okay, so in this case, the property, though I stated the induction template where the predicates are applied to integers, here also the predicate is applied to an integer, but the predicate Pn here could be thought of as the following statement, that for every object of size n, some property holds. Okay, so the predicate is basically stating that every object of size n has some property. Here I'm using size in a loose fashion. In our previous example, a size n grid, so the object was a punctured grid, and the size n punctured grid means it's a grid of size 2 to the n by 2 to the n, right? And the property was that it can be tiled using Trominos. So the predicate Pn, it's a statement only about a number n, but what it says is that for every object of that size, the property that it can be tiled using Trominos holds. And when we are trying to prove pk implies pk plus 1, right? You get to assume pk and you have to prove pk plus 1. But remember what pk plus 1 is saying. It says for every object of size k plus 1, some property holds. So you start off by saying, take an arbitrary object of size k plus 1. Okay, and then you have to somehow use your induction hypothesis to show that that arbitrary object has the property you are interested in. So how do you do that? So if you want to use the induction hypothesis, you need to, it applies to objects of size k, right? So what you can do is you can take your object of size k plus 1 and break it up into objects of size k somehow. In our case with the grids, you broke it up into four punctured grids, and to make sure they were all punctured grids, we also used a Tromino in the middle. So all 4 objects you got were of the smaller size, were of size k, and further they were all valid objects. They were punctured grids. And then you can appeal to the induction hypothesis and draw conclusions about the smaller objects, since the induction hypothesis says for every object of the size k has this property. You can say that all of these things that I got, they all have this property, namely they can all be tiled using Trominos, and then combine, then use that fact to derive that your original object has a property. So in our case, we said, you can just take all those tilings, combine it with the tile in the middle that you removed, and you'll get a whole tiling. Right? So that part was done, by pictures, but it should be clear that that holds. Right? So so the important thing here is that you had to take an arbitrary object of size k plus 1. Because remember, you're trying to prove that some property holds for every object of size k plus 1. And a very common mistake is, instead of taking an arbitrary object of size k plus 1 and breaking it down into objects of size k, a fallacy is to go in the opposite direction. You say, okay, let me take some objects of size k. So let me take some 4 punctured grids, and let me put them together into a larger punctured grid. But what's the problem with this argument? It's only talking about objects of size k plus 1 that can be derived by putting together objects of size k. Maybe there are other objects of size k plus 1 which cannot be derived in the way that you're deriving this larger object from smaller objects. So what you need to show is that every larger object can actually be broken up into objects of the smaller size. Okay? So that's something to watch out for, that you're not going in the opposite direction when you're making this proof. You do need to, say, take an arbitrary object of size k plus 1. Okay, let me conclude with this extension of the induction principle or induction argument we saw. So in strong, this is called strong induction. So in strong induction, we make our life a little easier. We prove P1 as before, but for all k greater than or equal to 1, instead of proving Pk implies Pk plus 1, you prove that P1 and P2 up to Pk together implies Pk plus 1. So you get to assume more things to prove Pk plus 1. So it should make your life easier, right? Of course, if you only can ignore these other things and just prove Pk implies Pk plus 1, but it gives you the extra flexibility of being able to refer to all of these and derive Pk plus 1 from that. So in terms of our picture, it looks a little bit like this, our program, right? So you have proven P1, and the induction step, what you proved is, the first one looks the same. You say P1 implies P2. And the second one is not saying P2 implies P3, but you say P1 and P2 together implies P3. And then this one says P1 and P2 up to P3 implies P4. Okay. So this, this should make it, these are slightly easier statements to prove potentially. So they are slightly weaker statements, seemingly weaker statements, but nevertheless, it's good enough to run our program. So first step is exactly the same as before. You use these two statements to derive P2. But for the second step, you can go back and use not just P2, but P1 and P2, because you've proven that, and use them along with this statement here to prove P3, and then use P1, P2, and P3 together to derive, P4, and so forth. And result of this program, the fact that this program exists, is taken as a proof that for all positive integers Pn holds, for all positive integers n, Pn holds. So this is called strong induction, or simply mathematical induction. So it's actually nothing new. It's the same as weak induction, but applied to a slightly different predicate than P. So if you imagine a predicate Q, where Qn is defined to just say, P1 and P2 and P3 all the way up to Pn. Okay, that is the definition of Qn. So if I define Qn to be the conjunction of Pm for all m in 1 to n, so there's a new predicate now, right? And if you apply weak induction to Qn, that is the same as applying strong induction to P. If you look at what the induction hypothesis is, right, it's saying it's saying P1 and P2 all the way up to Pk. That is to say, for all n less than or equal to k Pn, or in other words, it's the same Qk. Okay, so this is just Qk. We'll see a few examples of strong mathematical induction. So remember, this is what strong induction is. You need to only prove P1 holds and a statement that for every positive integer P1, 2, 3 up to k implies Pk plus 1. Then you automatically get to conclude that for every positive integer Pn holds. So the induction hypothesis here, is a stronger hypothesis, which makes it easier to prove things. Instead of compared to weak induction, where you only assume Pk, now you get to assume P1 to Pk. So we'll see why that is useful. So here is one example. Here's a claim. Suppose, the claim is that you can, suppose there are postage stamps of denominations rupees 4 and rupees 5, and the claim is that you can use these two stamps to make every amount as a positive integer, every amount of postage that is at least 12 rupees. So 12 rupees, 13 rupees, 14 rupees, any of them can be written as a combination of rupees 4 and rupees 5 postage stamps. Okay. So here is a claim in terms of just numbers. So for every positive integer, if the integer is greater than 12, then you can write it as a combination of 4 and 5. So 4a plus 5b using some non-negative integers a and b. So a and b could be 0 also, right? So the base case, so how are we going to prove? So I'm going to use the base, I'm going to write these as all base cases, not just one base case. I'm going to use several base cases. So n equal to 1 to 11 are all vacuously true. The interesting things start after that. N equal to 12 can be written as 4 times 3. 13 can be written as 4 times 2 plus 5. 14 can be written as 4 times 1 plus 5 times 2. And 15 can be written as 5 times 3. Right? So I went from everything between 4 times 3 and 5 times 3. I've written as linear combination of 4 and 5. Now, so I'm going to take all these as my base cases, and what I'm going to do, the induction step, is for proving things greater than or equal to 16. So as you already saw, it's a little more flexible than the way I stated it in the previous slide, where the base case is always for 1, and you have to prove for all k greater than or equal to 1, pk implies pk plus 1. It doesn't have to be that, right? As long as I will be able to fill in my table in the sequential order, I will be able to write a proof. So this can be shown to be equivalent to what is there, and you can reformulate this proof so that it is actually exactly showing that P1 and then pk implies pk plus 1 for some k greater than or equal to 1 for some more complex form of p. But it's convenient to just think of it as instead and then you get to do your induction step for all integers beyond the base cases, right? Okay, so for all integers k greater than or equal to 16, I'm claiming that I get to assume that this condition holds strictly less than, up to strictly less than k. So n strictly less than k. That's why I'm going to start with k equal to 16, so that something I have already shown for k equal to 16, that the claim holds for all n up to 15. Okay. So for k greater than or equal to 16, I'm proving that if the claim holds for all n strictly less than k, then it holds for n equal to k as well. Okay. So that'll let me, from my base case, it'll let me conclude that it holds for 16. Then once I have that, also it'll let me conclude it for n equal to 17 and so forth. Okay, so why is this? So k is greater than or equal to 16. So first I'm going to just remove a 4 from it. Okay, and what I'll be left with will be something greater than or equal to 12. By induction hypothesis, and it's greater than or equal to 12, and it is strictly less than k, right? So it falls in this range, and further, since it's greater than or equal to 12, actually it can be written as a linear combination of 4a plus 5b. So k minus 4 can be written as 4a plus 5b, so k is just 4a plus 1 plus 5b. So it's a very easy induction step once you know what you're going to do.